Alright, this is number 7 from the 2002 AP Physics B exam. This is a modern physics problem. And in the problem, we're given the momentum of a proton. We don't have to worry about anything dealing with relativity. And we want to know the de Broglie wavelength of that proton. Well, wavelength of anything with momentum. This could be Planck's constant over the momentum of the object. Planck's constant, 6.63 by 10 to the negative 34. That's joule seconds. Momentum, also given in standard units, so that's fine. 5.5 by 10 to the negative 20 kilogram meters per second. Do some simple math, and you're going to get 1.2 by 10 to the negative 14 meters. Now, this was A. We want to figure out for B the kinetic energy of the proton. Well, kinetic energy of any moving object is 1/2 mv squared. The mass of a proton is a given value in your information table, so we've got that, but we don't know the velocity. So we're going to come back to this. We're going to recognize that momentum is mass times velocity. I'm going to use this to solve for the velocity. So I'm going to be looking at the 5.5 by 10 to the negative 20 kilogram meters per second, and then we're going to divide that by the mass of a proton. The mass of the proton is 1.67 by 10 to the negative 27. When you do the math, make sure you toss this bottom number in parentheses. Otherwise, you're going to have some calculator issues. And we're going to get a velocity of 3.3 by 10 to the 7 meters per second. Now I'm going to use that up here in the kinetic energy equation. I'll do that work down below, though. So the kinetic energy of this proton is going to be 1/2 of the mass, still the 1.67 times 10 to the negative 27 kilograms. Now it's time the speed here that we just calculated squared. Don't forget to square that speed. And you're going to get a kinetic energy of right around 9.1 times 10 to the 13 joules, give or take a little bit due to multiple stages of possible rounding errors. Alright, and that's the kinetic energy of this particular proton. Now, we've got some new information. That proton heading towards the uranium nucleus starts off very far away, and then it eventually reaches a distance d from the center of the nucleus and then reverses direction. We're not going to worry about the effects of the motion of the nucleus after this happens. We want to know how far away is that value d. This, on the surface, might seem weird. Think about it. If you take a ball and you throw it up in the air, eventually it's going to stop in reverse direction. If you use that analogy, you might understand how to do this problem. You're going to take into consideration energy analysis. We're going to recognize that the energy in the beginning must equal my energy at the end. Energy is conserved. In the beginning, it was very far away, so the proton only has that initial kinetic energy. So there's no potential energy in the beginning, it's just kinetic energy. At the end, it eventually stops and reverses direction. That's a spot where we have no kinetic energy and we only have potential energy. So my initial kinetic must equal my final potential. Remember, potential is often written as capital U. My kinetic energy, we already know, so I don't need to put this into an equation. The potential energy, though, we do need to have an equation for. And you got to understand that this is electrostatic potential energy. So we're going to use K, Q1, Q2 over R. That R is the distance we're looking for. Q1 is the charge of the nucleus of the uranium atom. Q2 is the charge of the proton. Or switch those, it doesn't matter, it's a product. We're looking for D. So D is K, Q1, Q2 over the initial kinetic energy. Now, we know the charge of a proton is one elementary charge. What is the charge of this uranium atom? Let's look at the uranium. It's a 235-92, which means that mass is 235 The atomic number is 92. That means it has 92 protons in its nucleus, which means it must have a charge of 92 elementary charges. So we're going to say it's K, which is 9 times 10 to the 9, times the charge of the uranium nucleus, 92 elementary charges, times the charge of one proton, that's one elementary charge. I'm going to divide that by the 9.1 times 10 to the negative 13 joules. We can simplify this as 92e squared, or 92 times E again. It doesn't really matter. E is 1.6 times 10 to the negative 19 coulombs. Toss that in for E twice, or resimplify this to E squared and square this term. I'm not going to rewrite all this and plug it in. Ultimately, as long as you take care of your calculator work, use parentheses, be very liberal with your parenthesis usage, you're going to get 2.3 times 10 to the negative 14 meters. So that's the spot where it stops and starts to move away. It's like that ball getting thrown up in the air, stopping, and falling back down. Really, it's the same idea. D. After the proton is moved away from the nucleus, the nucleus spontaneously fissions. So let's go split up into these two elements and 3 neutrons. As a result, this energy is released. We want to indicate whether the mass of the uranium nucleus is greater than or less than the mass of the products. This first part is kind of a trick. I think they're expecting you to say that the uranium has lower mass than the products because you remember that whole mass defect bit. Well, that's not true. In both scenarios, taking products and turning it into an atom, or taking an atom and turning it into a product, both of these scenarios, mass is converted into energy, and we're going to lose some of that mass. So, first, let me clean up all this mess. But while I'm doing that, I can talk. Maybe I can't. I can't do two things at once. Of course, that's way off. Okay, no more cleaning up the mess. Anyhow, the uranium nucleus, or the uranium atom itself, must be greater than the products because some of that energy is lost during the fission process. We can calculate the mass difference, though, and instead of me cleaning up and moving it and looking all clean, I'm just going to do that work in this white space here. E equals mc squared. So the mass difference will be, well, if E equals mc squared, then it's E over c squared. And the E is the energy being released, 2.5 times 10 to the negative 11 joules. And divide that by the speed of light squared. And please, again, toss parentheses around this stuff so you don't screw up your calculator work. And we end up getting a mass, this would be in kilograms, of 2.8 times 10 to the negative 28 kilograms. It's obviously a very small amount of mass. You could then divide this by the value of 1U if you want to know how many universal mass units it is, to then use it to estimate if you were correct on the whole greater or less than part. I'm not going to do that, but you're welcome to. So this is the work for, what letter is this? D? Alright. And that completes our problem on the nuclear physics side of modern physics. Thank you.